Hey everyone, and welcome back to The Explainer. So, you know that feeling when you're working through a calculus limit and out of nowhere the math just breaks? The numbers stop making any sense, and the equation completely refuses to give you a clean answer? Well, today we are absolutely not accepting defeat. We're going to put on our detective hats and use some serious mathematical forensics to track down the true answer to a seemingly impossible limit.
That brings us exactly to the crux of our mystery today. What actually happens when math breaks and hands you a 0 divided by a 0? Your calculator screams error, and honestly, your first instinct might just be to pack it up and go home. But we need to reframe that thinking. 0 over 0 is not a dead end. Instead, think of it as a mathematical locked door that is absolutely begging to be opened. We just need the right key.
Here is our roadmap for this explainer. 1. The indeterminate trap. 2. Unlocking L'Hopital's rule. 3. The first derivative. 4. The second strike. And 5. The final solution.
This right here is our entire journey today. Now, I know it looks like a dense wall of calculus right now, but don't worry, we're going to zoom in and tackle it step by step until it makes perfect sense.
Section 1. The indeterminate trap. Falling into the 0 over 0 illusion.
Okay, so here's the specific problem sitting on our desk today. We need to evaluate the limit as x approaches 0 for the function 1 minus the cosine of x, all divided by x squared. Now, whenever we face a limit problem, our first intuitive strike, the most straightforward move, is to just take that 0 and plug it directly in for x to see what happens. Let's go ahead and do that direct substitution. The top becomes 1 minus the cosine of 0. Since the cosine of 0 is 1, the top is just 1 minus 1, which gives us 0. And the bottom becomes 0 squared, which is, 0. And there it is, 0 over 0. Math is basically throwing its hands up in the air here. This is what we call an indeterminate form. It doesn't mean the answer is undefined, but the form we currently have just isn't giving us enough information to figure out the real answer. We are officially caught in the trap.
Section 2. Unlocking L'Hopital's rule, the ultimate mathematical tool for indeterminate forms.
Now, what's genuinely amazing is the sheer power of this rule. L'Hopital's rule basically says that if you take the limit of a fraction and it results in an indeterminate form, like 0 over 0 or infinity over infinity, you are allowed to take the derivative of the numerator and the derivative of the denominator completely separately and then try taking the limit again. It's literally like a special permission slip from the calculus gods. And because our problem gave us exactly 0 over 0, we meet the exact condition needed to use this incredibly powerful tool.
Section 3. The first derivative, applying the rule for the first time.
All right, let's walk through the mechanics of this systematically. Step 1, we differentiate the top. The derivative of a constant, our 1, is 0. The derivative of negative cosine x is positive sine x. So our new top is simply sine x. Step 2, differentiate the bottom. Using a simple power rule, the derivative of x squared brings the 2 right down to the front, giving us 2x. Notice how that terrifying original function has completely transformed into something new, sine x over 2x.
Awesome. So, let's plug 0 into our shiny new equation and get our answer, right? We plug 0 into sine x, and the sine of 0 is, well, 0. We plug 0 into 2x, and 2 times 0 is 0. Oh man, total plot twist. We hit 0 over 0 again. The mathematical boss is somehow still standing, and we've fallen right back into the indeterminate trap.
Section 4. The second strike. When at first you don't succeed, differentiate again.
Now don't panic, because in calculus, when at first you don't succeed, and you still have a 0 over 0, you just differentiate again. Hitting that indeterminate trap a second time isn't a failure at all. It's really just an invitation to dig a bit deeper. Think back to our rule. Does the limit of our new function, sine x over 2x, result in 0 over 0? Yeah, it sure does. Therefore, the condition for L'Hopital's rule is still perfectly met. This means we can legitimately apply our exact same forensic tool a second time. We call this the double tap.
So let's narrate this second round of differentiation. Keep your focus here, because we're getting incredibly close to the truth now. Step 1. Differentiate the new numerator. The derivative of sine x, as we know, is simply cosine x. Step 2. Differentiate the new denominator. The derivative of 2x is just the constant, 2. Look at how much cleaner that is. Our function has beautifully evolved once again.
Section 5. The final solution. Reaching a definite value. Let's just compare the evolution of this function for a second.
We started with a complex, messy fraction that yielded 0 over 0. Our first application of L'Hopital's rule stripped away some of that complexity, leaving us with sine x over 2x. Still indeterminate, sure. But our second application, the double tap, stripped away the problem entirely. It left us with this super simple, elegant function, cosine x divided by 2.
And now for the deeply satisfying conclusion. We take our original limit, x approaching 0, and we plug it right into our final stage function. The top becomes the cosine of 0, and the cosine of 0 is exactly 1. The bottom is simply the constant 2. 1 divided by 2, 1/2. We did it! We finally escaped the indeterminate trap and arrived at a definite, concrete value. The limit is 1/2.
Which really leaves me thinking, what other seemingly impossible mathematical dead ends are out there just waiting to be solved simply by taking another derivative? It's a great reminder that when a problem looks totally unsolvable at first glance, it often just requires a bit of persistence, a cool head, and exactly the right tool for the job.
Before we wrap up the explainer today, I want to give full credit to the creator who originally mapped out this elegant mathematical solution for us, Raiz Amav Bhatt. Thank you all so much for joining me in breaking down this calculus mystery. Keep questioning, keep calculating, and I'll catch you in the next explainer.